Today what we're going to do is what we call color changing milk. It doesn't sound very nice, it doesn't sound like it's an amazing experiment, but I guarantee you if you do this at home, your jaw will kind of drop the first time you do it because it's really, really cool and it's really, really colorful looking. So everything for this experiment you probably already have in your house. The first thing you'll need is some kind of a plate to hold the mixture, right? So a paper plate is fine. You'll need a glass of milk, right? You will need some detergent, some dish soap. This is what we use in the kitchen counter and the sink. This is Dawn dish soap. You can use anything you like, but Dawn seems to work the best. You will need some food coloring, right? I have 4 different kinds here. They usually come four to a box, so any color works fine. You can use one color or all 4 colors. And then you will need also a cotton swab. So as you can see, everything we have here is something that most people probably have in their kitchen. So what I'm going to do is rearrange things here. Okay, now what we've done here is put our plate front and center and moved all of our other ingredients off to the side so we can see what happens. The first thing you want to do is put your milk in the plate. Now this milk, you can use really any kind of milk you want. There's nothing special about it. It works better with whole milk than it will work with 2% or fat-free milk, and you'll see why in just a minute. So use regular whole milk, and what you do is you just pour it into your plate until you get a nice little layer. Just a thin layer like that is really all you need. You can do a little bit more if you like, right? So make sure the entire bottom is covered. And what I like to do is give it a nice count to 10 or so, because what you really want is for this milk to not be moving at all. You want it to be completely motionless. So 5, 6, 7, 8, 9, 10. So it's been sitting there. We don't see any bubbles moving. The next thing you want to do is take your food coloring. Here I have, again, 4 different kinds of food coloring. It doesn't matter, you can use your favorite colors. And what we're going to do is put some drops. We're not going to spread them out, we're just going to kind of put some drops right on top of each other until we have a nice little red dot there. Here is blue. And you want to try to keep them separated. It'll make it a little bit more impressive as you'll see in just a moment. So we have the nice blue drop here. And then we're going to do the green drop right below. Like that. And then finally, I guess you could call this orange. And some food coloring kits may have different colors. It all works just fine. Really, the food coloring doesn't have anything to do with this experiment. The only reason we're putting food coloring in is so we can see what happens. Because milk is white, and so what's going to happen in a minute, the milk's going to start moving, we want to be able to see it. The next thing you want to do is take your Dawn dish soap, or whatever dish soap you have, and a cotton swab, and you want to dip it in there. You don't want a thick glob like that. You want to kind of work it off on the side until you have a good bit of soap there, but it's not dripping off. Okay, just like this. And then I want you to watch carefully as we actually place that inside of the milk. Watch carefully what happens at the moment we push it in. Here we go. 3, 2, 1, go. Look at that. The milk just kind of goes nuts. It completely spreads out. The green kind of completely intersected everything else, and it goes out. Let's go over here to the orange and touch the orange and see what happens. The orange flies everywhere. Okay? We'll go over here to the blue. The blue goes everywhere. So notice that as we're holding it here, the milk continues to move. You see it's continuing to move out from the point. We're not really moving the Q-tip. The Q-tip is staying motionless, but the milk is going. Now we can use the other side of the Q-tip to kind of get a fresh, see if we can get it going even better. And let's see what happens. We'll try this side over here, and that starts to move. Basically, wherever you touch this Q-tip, the milk food coloring solution is going to tend to move out away from it. Now notice what's happening now. As I do it more and more, the effect is not as strong. See, when I first put that very first dot in there, things moved really, really rapidly, and now I can just grab a whole bunch of soap and just drop it in there, and not that much is happening. You can see it's not really doing the same thing. So you have to ask yourself as a scientist, how is this possible? How is this working? Well, obviously, it's an interaction between the milk and the soap, right? Because the food coloring, we had the food coloring in with the milk, and nothing happened. It just sat there. At the moment we dropped soap in there, it started radiating and going away from the point that we put the soap in there. We didn't have to move the soap around. We just stuck it in there, and the milk just continually kind of shoots away from the point that we put it in there. And also, as we do it more and more and more and more and more, basically the experiment stops working. So that's kind of going to factor into what's going on here. what's happening is, this is an example of how soap really works. Notice, what do we use soap for? We use it when we have our hands that are greasy, maybe we've got some fat or something on our hands or some oil, and we want to get rid of it, right? So if you put that under water and you try to wash your hands without any soap, and you have really oily hands or fat hands or something on your hands that's really fattening, it's going to be difficult to get off. But you put a good quality dish soap on your hands, you rub them around really good, you put them under the sink, and you can actually start to feel your hands getting clean. What's happening there is this soap is not just a blue formula in the bottle, it's specially made to basically bond to those fat molecules and to those proteins that are in things like bacon grease and things that are in like oil and such like that. In this case, there's also fat inside the milk, and there's also proteins inside of the milk. That's one of the reasons why milk is so good for you, right? So what's happening whenever you wash your hands is that soap is bonding. It's actually connecting to the fat molecules, to the proteins. It's actually bonding to those molecules, and then the water is able to wash it away. So it kind of goes out there and it latches on to those molecules of the fats, and then the water actually is able to wash it away. In this case, we have a nice surface of milk, right, which has fats and proteins baked into the milk. That's just part of the milk. We put the food coloring there just so we can see what happens. And at the moment that we put the Q-tip into the solution, what happens is the soap starts to bonding with those proteins, and it causes the milk to start to move, because what happens is those proteins and those fats, they you can sort of think of them as being agitated. They're bonding to that soap, they're moving away from the soap, and they start to swirl because of the chemical reaction with the soap, the same way that we're able to wash our hands clean. That's part of what's happening. The other part is that the soap actually breaks down the surface tension of the milk. So if you look carefully at a glass of water or at a glass of milk, you can kind of see that skin that's right on top. You know, you can kind of dip your finger into the very top of a cup of milk or a glass of water, and you'll see the skin there on top. We call it the surface tension. That's just because of the water that's inside of the milk and the way that it bonds, right? And it creates that kind of skin. Soap immediately destroys that skin. That surface tension, and that's just because of the reaction that's going on as well there, the bonding that's going on. So there's two things. The surface tension is disrupted, and also the fats and the proteins start bonding with the soap. Those two things together cause the milk to physically start to move because of all the agitation going on and trying to bond with the soap that we're just putting in the water, and it starts to move away from the point that the soap is put, right? And that is the reason why the milk starts moving. The food coloring has nothing to do with it. Food coloring is mostly water. The only reason we put food coloring in is so we could actually see the swirling motion. So that's the science behind it. It's actually bonding the soap with the fats, and that's causing, along with the surface tension, causing the milk to start to get into motion, and that's why we see the nice colorful changes there. You can do this over and over and over again with a new batch of milk. However, notice that the experiment, the chemical reaction really stopped working. We can put it back in there. You can see it doesn't really do anything. The reason is that as the milk starts to mix, the soap that we're putting into the milk starts to mix with the body of milk that we have. So in other words, after the swirling continues for a while, the soap that we're putting in there gets mixed in with the milk, and then of course everything's already happened. So you can't just continue adding soap because all of the fats have already bonded, everything's already done, the surface tension's already not really the same as it was, and so the effect is not going to continue. So to do this experiment again, you'll need to get a fresh plate with fresh milk, with fresh soap, and fresh cotton swabs here to continue doing it. But it's really, really cool. Kids love it, and it's a great way to explain what basically a molecule is. The fact that you have these invisible things, they're bonding together, it's causing this motion, is a really neat way to learn about this stuff. I'm Jason with scienceandmath.com. Go grab these materials. It takes literally 5 minutes, and I promise you the first time you do it, I think you'll be surprised at what you see. Learn anything at mathandscience.com. And today we're going to do a really neat experiment, very simple to do. We're going to take a glass bottle, we're going to take a hard-boiled egg, and we're going to try to fit this egg inside of this glass bottle, which it doesn't seem to be able to do, and we're going to use the power of air pressure in order to make that happen. So what you need for this experiment to pull it off is very, very simple household items. You'll need a hard-boiled egg. Go ahead and boil it ahead of time and peel it also. It's peeled as well. We need a few matches, so what we want is the wooden matches. and you'll see why we need that here in just a minute. And then you'll need a glass bottle. This guy came from Starbucks. You could use any glass bottle you want. You just need to make sure that the egg cannot fit inside. Otherwise, you won't be able to do the experiment. And you also want to make sure that we get any kind of adult permission, parent permission for this experiment as well, because we're obviously using some matches, so we want to make sure and get permission as well. So we'll put our safety glasses on. Now what we're really going to do in this experiment is we're going to set our bottle up. We're going to take 3 matches, 3 wooden matches out, and essentially what we're going to do is light our 3 matches, throw them in the bottle, and then get the egg on top. Now one thing you want to make sure and do, you don't want to be reckless with this, but when you light the matches and you get them in the bottle, you really want to get them in there pretty fast. You don't want the flame to cool off too much. You want to get it in while it's nice and hot and then get this egg plugged in. Also, when you put the egg on top, you want to make sure and put the small end of the egg, the pointy side, so to speak, down like this, right on top. So let's go ahead and do it. It's going to happen sort of fast, so I want to make sure to explain it. We're going to light it, get them in there, and then get that egg on top pretty fast. So let's go ahead and do that now. 1, 2, 3. Light, inside, egg on top. And then we'll see what happens. Notice the egg just goes right into the bottle, just like that. Now, you can do this over and over again. Most kids, when they see this, are kind of amazed because obviously the egg doesn't, we can go ahead and take our safety glasses off now. The egg doesn't fit through the bottle. So the question you have to ask yourself is, why does lighting a few matches and putting them inside the bottle do anything at all? And the answer is, that all around you we have air pressure. And you don't feel air pressure because of the way your body works, but it's all around us. I mean, if you think about it, and there the egg goes and drops into the bottom. When you think about it, you're sitting on Earth, and all above you is a giant atmosphere of air. We don't think about air weighing very much, but it actually does exert pressure and push down on top of everything, right? And it's quite a bit of pressure. The reason you don't feel that pressure is because the inside of your body has liquids and they also exert pressure. So the inside of your body and the outside air are pushing back and forth to one another, and so you don't feel that the air is really pushing on you that much, but it actually is. And we're going to use that force, that pressure of the atmosphere to get this egg in the bottle. The trick is what we want to do is somehow create a low pressure inside of this bottle so that we'll have a low pressure inside and a high pressure on the outside, and then the pressure will push the egg inside the bottle. And the way we do that is with these matches. It doesn't seem like it would work at first, but what happens is when you light a match, it makes the air hot, right? If you just hold a match up and the flame is going, it's getting the air hot. When you light these 3 matches and you put them inside the bottle, it makes the air inside of this bottle hot. Now, what happens to hot air when you heat it up, or what happens to air when you heat it up? It wants to expand. It wants to get bigger, right? If you put something in the freezer and cool it off, it wants to get smaller. It wants to contract. But when you put things in flames or in heat, they want to get bigger. So as soon as we put this match in the bottle, the air in here wants to get bigger, and some of it basically pushes out of the top of the bottle here. And so once we plug it up with the egg, the flame goes out, right? And the air that's remaining, it was hot just a few seconds ago, but as soon as we plug it up, it starts to cool off. What happens to things when they want to cool off? When a gas cools off, it contracts, it gets smaller. So because we made the inside hot, thereby pushing some of the air out of the bottle, and then we plugged it up, and then suddenly it cooled off on the inside, all the air wants to contract inside, and that creates low pressure. Low pressure just means less force of the air inside of there. So you have a small pressure zone inside of here, which means less air pressure, and you have the atmospheric pressure, which is always outside, and you have more pressure outside than inside, and that just rams the egg through there. And you notice it just kind of gradually just draws it in. The more this air cooled off inside, the more force that we had to push that egg in. So it's all about balancing air pressure, And that's what's happening in this experiment. So go grab yourself a hard-boiled egg, go grab yourself some matches, go grab yourself some safety glasses and an adult, and go ahead and do this experiment, because it's really a lot of fun, and it really demonstrates about air pressure around us. The only thing I can really tell you as far as helpful hints is when you put the matches in, try to get them in there fast. If you light the matches and just sort of watch them burn and watch them burn, and then you put them in there, the effect is not going to be as good. You want to get those matches in there when the flame is the hottest. So light them, get them in there, get the egg on top, and I think you'll see this experiment work every single time and enjoy the results.
Learn anything at mathandscience.com.
Today's experiment, what we're going to do is learn how to use a piece of string to lift an ice cube out of a glass of water without tying that string to the ice cube at all. And it's very simple, and if you do it in the right way to your friends or to your parents or somebody like that, then you can actually have a lot of fun with it because there's really kind of a wow factor to this little very simple experiment. All you will need for this experiment is a piece of string. Any type of string will do. You need some regular ice cubes, you need a glass of water, and you need regular old table salt. So nothing more fancy than that. It's all things that you have usually in your house right away. So let me go ahead and put my safety glasses on. There's nothing too dangerous here really, but we want to just be getting in good habits. What you want to do is take your salt and kind of keep it out of sight. You don't want whoever you're showing this to see the salt. It's kind of a little bit of the mystery here. So let's go ahead and take our string and put it to the side. The way you want to do this, the way you want to set this experiment up basically, is you want to have a glass of water. It's just regular tap water, and you can even actually fill the glass with water directly in front of the people that you're doing this for, just so they know that there's no tricks and there's nothing going on, no funny business, so to speak. What you want to do is basically take your glass of water and keep it separate from the ice, and right in front of the people you're doing this for, just take a regular ice cube and drop it in the glass of water. Now you can actually put a few pieces of ice in there if you want, but just for the sake of this demonstration, I'll just use one piece. It'll be a little easier to see what's happening. And what you do is you approach the people and you say, I bet you that I can take this ice cube out of that glass of water with this piece of string, and I will not touch that piece of ice with my fingers at all. Because most people, when they see this, they'll say, well, he's going to tie the string to it, he's going to do something like that. But you tell them, no, I'm not going to touch that ice at all. I'm going to use this string, I'm going to take that ice out of the water, and I'm not going to touch that piece of ice. Most people will say, that's impossible, you can't do that. And you'll say, watch me. So what you'll do then is out of your back pocket, you'll pull out some table salt. And this is sort of the secret ingredient to make this work. So what you'll do first, though, is what you need to do is lay this piece of string across the top of the ice. It doesn't matter exactly how it's done, but you did promise that you wouldn't touch the ice with your fingers, so you don't want to touch the ice with your fingers. So just kind of lay it across the top, much like I have it here, right? Obviously, you're not going to be able to do anything with it. You're not going to be able to pull the ice out now, but then what you do is you sprinkle the salt right on top, like that. That's all you need, and you count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then carefully and gently you lift this ice cube out of the water. And that's it. This ice cube has frozen itself. Whoops, there it fell off there a little bit at the end there, but it lifted itself out of the water. Let's do it one more time just to kind of show you how to do the whole thing. We'll put a few more ice cubes in, just kind of give it some variety. So now that you know how to do it, just lay the string. You can actually coil it up even. It's a little bit better sometimes. Just lay it across there and then goose it really good. Everywhere where the string is touching an ice cube, you hit it and you count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's like going fishing. You just see what you get in the end. Sometimes you get lucky, like this. And on the bottom one there, we didn't quite manage that one, but here we did lift that guy out. So that's a pretty amazing trick, right? You're able to lift, and it's frozen. It's frozen solid to this guy. So how does that work? I mean, if you don't use the salt, obviously it doesn't work at all. If you just take a piece of ice in there, there's no salt, you can hold it there all day, it's not going to refreeze to the string. So obviously the salt has something to do with it. How does it work? Okay, when you put salt, regular old table salt, on ice, it has an amazing effect, a really amazing effect. What it does is it changes the freezing point of the ice. And the reason that it does that is kind of beyond the scope of this video. It's deep into the way that ice is formed. But the bottom line is that if you think about ice, what is ice? It's frozen water, right? So if you take water and you put it in a freezer and you lower the temperature to the freezing point, which is 0 degrees Celsius, or you can also talk about Fahrenheit, 32 degrees Fahrenheit, then once you reach that 0 degrees Celsius, then it's going to crystallize and form this solid that we call ice that we see every day, right? Okay, now the deal is that whenever you put that salt on the ice, then at that moment, at the point where the salt touches the ice surface, the melting point or the freezing point of the ice is no longer 0 Celsius anymore. It's lower than that. You've lowered the melting point. And again, the reason why is deep in the reasons of how ice is formed and the interaction with the salt and all that, but you've changed the freezing point. So, to use my hands to gesture a little bit, let's say this is 0 degrees Celsius. So here we have some water. It's warmer than that because we just put it in the freezer. The freezer cools off the ice. It gets to 0 degrees Celsius where my hand is. Suddenly it forms ice cubes, all right? Now, if we put salt on this ice, we lower the freezing point even more. So suddenly that ice is not cold enough to be frozen anymore, right when we put the salt on there. So what happens is when you put salt on ice, the net effect of it is the ice melts right at the portions and right at the point where the salt crystals touch the ice. It actually melts. If you could get a microscope and look at this ice right at the moment when I put the salt on it, you would see the very top layer of that ice gently begins to melt. What happens is we put the salt on top of the string and it melts the ice gently around that piece of string, and it dissolves. That salt dissolves into the little bit of water that's on top of the ice cube right there when you sprinkle the ice on. After a few minutes or after a few seconds, that water dissolves that salt that you put on there, and it kind of runs off of the ice cube into the glass of water. So the salt is kind of carried away after a few seconds. And so the ice cube that's underneath it is still pretty cold, and it can refreeze the liquid water on top around that string, and that is what allows you to lift it up. So the bottom line is when you put the string on there and you put the salt on there, the only thing the salt does is really just gently melt a very small amount of that ice on top. The salt is then carried away by the liquid water, and then that remaining water that's left over is allowed to refreeze from the cold nature of the ice cube underneath. It gently refreezes just enough around that piece of string so that you can lift it up. Very simple experiment, but it illustrates something very important, and that is that salt has the ability basically to melt ice. So if you live in a cold environment, you might notice that on bridges, when it gets wintertime and the bridges are iced over, you'll see the trucks out there and they'll be putting the salt on the side of the road. The reason they're doing that is when you put salt on ice, what does it do? It lowers the freezing point. So if it's hovering right around freezing outside, just icing over your bridges, if you go salt your bridges, suddenly at those places on the bridge, ice cannot form at 0 degrees Celsius. It takes it a little bit colder temperatures to form that ice. So if your weather pattern is hovering around freezing temperatures and you put ice on the bridge, you should be able to prevent the ice from forming by putting the salt on the bridge there. And so that's why we do that. I'm Jason with scienceandmath.com. I hope you've enjoyed this. Go get these materials. It takes 5 minutes. It's actually really neat, and I think you'll find that if you show other people this guy, most people will not know how you're going to do it until you show them how to do it. It's a little bit of science here in everyday life that we can use to kind of have a little bit of a wow factor and impress people.
Learn anything at mathandscience.com.